Sometimes a single idea, written down on a research paper, can change absolutely everything. That's the story we're digging into today. It's about a paper from 2003 that laid the groundwork for, well, the entire big data revolution and the cloud as we know it. We're talking about the Google File System, or GFS. It was built to solve a problem so massive, it was literally breaking the internet.
So think about it. For Google, back in the early 2000s, this wasn't some kind of fun thought experiment. It was a full-blown crisis. Their web crawlers were just gobbling up the internet, creating data sets on a scale nobody had ever seen before. They desperately needed a way to store all this stuff, a file system that could actually keep up.
And here's the real kicker. They weren't doing this on some fancy, super expensive, ultra-reliable government supercomputer. No way. They were building their entire empire on thousands of cheap, off-the-shelf PCs. The kind of hardware that is pretty much guaranteed to have something break on any given day.
To give you a sense of the scale here, the paper itself talks about clusters with over 1,000 machines, managing hundreds of terabytes of data. And remember, this is back in 2003. They were staring down a data explosion, running on unreliable hardware, and every single tool they had was just falling apart.
So, how in the world do you solve a problem like that? Well, you don't do it by just tweaking what already exists. You do it by tearing up the rulebook and starting fresh. The GFS solution came from a completely new design philosophy, one that was born from looking at the crazy reality of their situation. This first idea is a total game changer. Think about it. Most systems are designed to avoid failure. GFS was designed to expect it. The system assumed things would break all the time. So constant monitoring, finding errors, and recovering automatically weren't just nice features. They were the absolute core of the design from day one.
Second, they noticed their data just wasn't normal. They weren't storing, your typical Word docs or spreadsheets. No, they were dealing with these monstrous, multi-gigabyte files that held countless web documents. The system had to be built for giants. And this third insight is just brilliant. They saw that once these giant files were created, people rarely went back to change things in the middle. Instead, new data was almost always tacked on to the end. It's a process called appending, and that specific pattern became the key to making the whole system incredibly fast.
Okay, so let's put it all side by side. On the left, you've got the old way of thinking. Hardware is reliable, files are small, you write data all over the place. But on the right, that's the GFS world. Hardware breaks constantly, files are gigantic, you mostly add data to the end, and getting a ton of data through the pipes is way more important than how fast you get the first byte. This new reality required a whole new architecture. So what did this new architecture actually look like? Well, it was surprisingly simple, really elegant. You had one master server and then a whole army of chunk servers. The best way to think about it is like a super efficient librarian running a massive library.
That single master server? That's our librarian. Now, the librarian doesn't hold any of the actual books, the data, but it knows everything about them. It has all the metadata, the file names, who's allowed to read them, and most importantly, it has a map that shows exactly where every single piece of every file is. It's the brain of the whole operation.
And the chunk servers? Well, those are the bookshelves. These are the thousands of regular computers that actually store all the data. The system takes those giant files, breaks them up into big, fixed-size pieces called chunks, and then scatters those chunks all across the bookshelves, ready to go.
So let's see how it all works when you actually want to read a file. First, your computer asks the master, the librarian, "Hey, where can I find the data for this file?" The master looks at its map and replies with the locations of the chunk servers. And then, and this is the secret sauce, your computer goes and talks to the chunk server directly to get the data. The master just points the way and then gets out of the way, which means it never becomes a bottleneck.
This whole setup is pretty genius, but there are two specific design choices that really made it work at such an incredible scale. It all comes down to the size of those data chunks and how the system made sure nothing ever got lost.
So just how big were these chunks of data? At the time, a typical file system was thinking in kilobytes. GFS decided on a chunk size of 64 megabytes. For 2003, that number was just ridiculously, mind-bogglingly huge.
Yeah, this slide really puts it into perspective, doesn't it? A 64 megabyte chunk is thousands of times bigger than a standard block. And the benefit is so simple. For one of their giant files, a computer could ask the master for a chunk location just once, and then get a massive fire hose of data back. It dramatically cut down on how often anyone needed to bother the busy librarian. Okay, so how does all this tie back to that failure is the norm idea? Easy. Replication. Every single 64 megabyte chunk isn't just stored in one place. By default, it's copied 3 times. And these copies are stored on different machines. And not just that, on different machine racks. That way, if a whole network switch dies, your data is still safe. The master is constantly checking on these copies, and if one disappears, poof, it automatically makes a new one somewhere else.
The ripple effect from these ideas is it's hard to put into words. The concepts from this one paper didn't just stay inside Google. They leaked out and became the foundational building blocks for so much of our modern world.
I mean, just look at this chain of events. GFS comes out in 2003. Right after that, Google releases papers on MapReduce for processing data and Bigtable, a database built on GFS. Those 3 papers together lit a fire under the open source community, which led directly to Apache Hadoop. And Hadoop's file system, HDFS, it's a direct descendant of everything we've just talked about.
So what are the big lessons we can pull from GFS today? First, design for failure. Don't fear it. Embrace it as part of the plan. Second, build your infrastructure and your applications together. GFS worked because it was perfectly tuned for what Google needed. And finally, if you want to solve problems at an insane scale, you have to be willing to break the rules and question everything you think you know.
The GFS paper solved a huge problem for its time by completely redefining what big even meant. But, technology never stops moving. And that leaves us with one final thought. The next giant leap forward is probably going to come from someone who looks at today's biggest challenges and asks, okay, what are the assumptions we need to break now?